Imagine staring at the night sky and realizing everything you thought you knew about reality might be wrong. Not a little wrong, fundamentally off. What if the universe we've been mapping for decades isn't expanding at the speed our best theories predict? What if the very fabric of space-time is whispering secrets we haven't learned to hear yet? That's exactly what one of the world's leading cosmologists, Nobel Prize-winning physicist Adam Riess from Johns Hopkins University, has been grappling with. He's spent his career chasing the expansion rate of the cosmos. And after poring over the latest data from humanity's most powerful eye in the sky, the James Webb Space Telescope, he delivered a sobering message. We have misunderstood the universe. Not hyperbole, not clickbait. This is a scientist reading his own precise measurements and admitting the elegant standard model of cosmology, the framework that's guided us for nearly a century, is showing deep cracks. Today we're diving into this cosmic puzzle. We'll explore the stubborn Hubble Tension, the surprisingly mature galaxies that appeared too early, the strange shapes of the infant universe, and what it all might mean for our place in reality. Stick around until the end, because this isn't just about distant stars, it's about rethinking how we see everything, including ourselves. And trust me, the implications will blow your mind. For generations, cosmology rested on the standard model of cosmology, often called the lambda CDM model. It weaves together the Big Bang, inflation, dark matter, and dark energy into a remarkably coherent story. From the first fractions of a second after the universe's birth, through the formation of the cosmic microwave background, CMB, that faint afterglow when the universe was just 380,000 years old, to the large-scale structure we see today, this model has used test after test. It predicted the right mix of light elements like hydrogen and helium. It explained how galaxies cluster across billions of light years. It even accounted for the accelerating expansion discovered in the late 1990s, attributed to mysterious dark energy making up about 68% of the universe's energy budget. Dark matter, another invisible player at roughly 27%. It provided the gravitational scaffolding for galaxies to form. Then JWST powered up in 2022, and the story got complicated. The trouble centers on one crucial number, the Hubble constant, H0. This measures how fast the universe is expanding right now. You'd expect two independent ways of calculating it to agree. They don't. One method looks backward in time using the Planck satellite's ultra-precise map of the CMB. Scientists take the conditions of that early baby universe, plug them into the standard model equations, and fast forward 13.8 billion years to predict today's expansion rate. Result? About 67 kilometers per second per megaparsec. Kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light years. So, for every megaparsec farther away a galaxy is, it's receding about 67 kilometers per second faster due to expansion. The second method is more local and direct. Adam Riess leads the JWST team, which builds a cosmic distance ladder. They start close to home with Cepheid variable stars, pulsating stars, whose brightness rhythm reliably tells us their true luminosity. Compare that to how bright they appear from Earth, and you get accurate distances. Next rung, galaxies containing both Cepheids and Type 1. A supernovae, exploding white dwarfs that all peak at nearly the same brightness, acting like standard candles. Calibrate those supernovae with Cepheids, then spot them in far more distant galaxies to measure recession speeds. Riess's team consistently gets around 73 to 74 kilometers per second per megaparsec. That 6 to 9% gap sounds tiny, but in precision cosmology, it's huge. It implies the universe might be a billion years younger than thought. reshapes distances to galaxy clusters, and challenges our understanding of dark energy, the force supposedly driving acceleration. Personally, I find this fascinating because it highlights science at its best, not as a monolith of certainty, but as a living, self-correcting process. We've spent decades assuming our model was nearly complete, yet nature keeps throwing curveballs. This tension isn't new. Edwin Hubble's original 1920s estimate made the universe seem younger than Earth itself, sparking decades of debate between camps favoring 50 or 100 kilometers per second per megaparsec. By the 2000s, it seemed settled around 70. Precision instruments revived the split. My analysis. This discrepancy forces us to confront a deeper question. Are we missing new physics in the early universe? Or is our measurement toolkit still flawed in subtle ways? Riess himself has emphasized that with JWST, confirming Hubble Space Telescope data on Cepheids ruling out issues like stellar crowding or blending, the error bars have shrunk dramatically. In a 2024 paper, his team analyzed over 1,000 Cepheids across multiple galaxies, extending out to 130 million light-years, and the higher rate held firm. Let me make this relatable with a couple of stories that ground these abstract numbers in human experience. First, picture a team of astronomers like Riess's SH0ES group, huddled in control rooms late at night as JWST data streams in. One young postdoc, staring at infrared images sharper than anything Hubble could deliver, realizes the Cepheid stars look exactly as bright, or dim, as before. No blending correction needed. The expansion rate isn't budging. It's like meticulously building a house of cards for years, only to watch the foundation shift slightly but stubbornly. That moment of, the data says what it says, is both exhilarating and humbling. I've heard similar tales from physicists who describe it as the scientific equivalent of a plot twist in your favorite thriller. A more vivid analogy comes from everyday life. Imagine two GPS apps giving you different arrival times for the same trip and says 30 minutes, the other 32. At first you blame traffic data. Then you realize the roads themselves might be changing in ways your maps don't capture. That's the Hubble tension. Two reliable navigators, CMB versus local ladder, disagree on the universe's speed limit. Now, let's talk about the early galaxies that shocked everyone. JWST peered back to when the universe was just 500 to 700 million years old and found massive galaxies that seemed to rival the Milky Way. In our cosmic neighborhood, it took about 13 billion years of mergers, gas inflows, and star formation to build something that size. Here were adults in a cosmic kindergarten. One real example, the so-called little red dots, compact, reddish objects initially flagged as impossibly massive. A graduate student named Katherine Swarovski at the University of Texas led work showing many weren't overflowing with stars at all. Instead, supermassive black holes at their cores were gorging on gas, heating it to glow brilliantly. From billions of light years away, that accretion disk light mimicked the output of billions of stars, inflating the apparent mass. It was like mistaking a powerful spotlight for an entire city. After correcting for these, the remaining galaxies still appeared more numerous and structured than expected, about twice as many massive ones. Another striking find, a massive spiral galaxy nicknamed the Big Wheel, spotted within the first 2 billion years. Spiral arms usually require calm, orderly evolution over eons, not the violent mergers expected in a chaotic young universe. Astronomer Tamiya Nanayakara noted it either formed its mass unusually neatly or built most stars in place without typical collisions. Contrast that with other JWST observations of 250-plus early galaxies. Many were clumpy, turbulent messes without settled disks. So the early universe hosted both messy teenagers and at least one remarkably mature spiral. That's not a clean contradiction, but it bends our expectations. Then there are the elongated, cigar-shaped galaxies. A late 2025 study found many young systems stretched out in ways cold dark matter models struggle to explain. These prolate shapes align better with alternatives like warm or wave dark matter, where particles behave differently, smoothing filaments and allowing gas to flow in elongated streams. My personal insight here: these findings remind me of exploring a new city. You expect grid-like modern streets, but discover a mix of chaotic old alleys and surprisingly elegant boulevards. It doesn't mean your map is useless. It means the city grew in ways influenced by factors you hadn't fully modeled, like hidden geography or cultural quirks. In cosmology, dark matter is that hidden geography. If it's not purely cold, slow-moving, clumpy, the scaffolding of structure formation changes, rippling through predictions for galaxy clusters, dwarf galaxies, and gravitational lensing. There's also the quieter S8 tension, about how clumpy matter is distributed. Direct measurements show slightly less clustering than the model predicts. Riess has called it the Hubble Tension's little sibling. If both are real, they might point to the same underlying physics gap. Adding my analysis, these anomalies aren't failures, they're invitations. Science progresses when data refuses to fit neatly. Think of the 1990s crisis when the universe seemed younger than its oldest stars, resolved by discovering accelerating expansion and dark energy. What looked like a fatal flaw became the doorway to a bigger picture. JWST is doing the same now. They're pushing us toward possibly new ingredients or processes in those unseen early epochs. Let's add some fresh perspective. The standard model isn't collapsing. It's too successful for that. It still nails the CMB, element abundances, and large-scale clustering. But these cracks suggest incompleteness. Possible fixes include early dark energy, a hypothetical burst of extra expansion right after the Big Bang that tweaks early conditions without wrecking later successes. Cosmologist Mark Kamiankowski likened it to the universe getting an unexpected kick at birth, whose effects ripple forward subtly. Alternative dark matter models, warm or self-interacting, could reshape how structures form, explaining both faster local expansion and odd galaxy shapes. Some theorists even ponder varying fundamental constants or modifications to gravity on cosmic scales, though these are riskier as they must preserve the model's many winds. In my commentary, this moment feels profoundly human. Here we are, a species on a tiny planet, using mirrors and math to argue over a 6% discrepancy in cosmic speed. It's absurd in scale, yet magnificent in ambition. It shows our drive to understand isn't just intellectual, it's existential. If the universe is stranger than we suppose, as J.B.S. Haldane might say, then our maps must evolve. Future tools like the Nancy Grace Roman Space Telescope, Euclid mission, and improved Gaia data will refine distances and maps of dark energy. The Atacama Cosmology Telescope has already nudged CMB estimates slightly higher, but not enough to resolve everything. What excites me most is the productive anxiety. No panic, just focused curiosity. Riess and others stress taking the problem seriously now that multiple instruments align on the data. But we're living inside a grand question mark spanning 14 billion years of unobserved history. Something new particle, force, or space-time property might be hiding there. In the end, the universe isn't broken. Our understanding of it is simply incomplete, like a jigsaw puzzle where one piece doesn't quite fit the box image. That mismatch doesn't invalidate the puzzle. It hints the full picture is richer, stranger, and more beautiful than we imagined. The clear lesson here? Embrace uncertainty as the engine of discovery. In science and in life, when data challenges your model, don't double down on old assumptions. Investigate, refine, and stay open. The crisis in cosmology isn't an ending. It's a door opening to the next chapter. What seems like a contradiction today may reveal deeper truths tomorrow, just as dark energy did decades ago. So next time you look up at the stars, remember, they're not just lights in the dark. They're clues in an ongoing conversation between humanity and the cosmos. Now keep asking questions, keep pushing the boundaries. The universe is waiting to surprise us. Thanks for joining this cosmic journey. If this made you rethink reality even a little, hit like, subscribe, and share your thoughts below. What do you think is missing from our model? I'll see you in the next one, where we might explore even wilder frontiers.